Today we're going to look at how adding heat affects an object. In a previous lesson, we learned that temperature is the measure of how hot or cold an object is, and it's directly related to the average kinetic energy of a single molecule. Today we're going to look at internal energy, known as U, is the sum total of all of the energy of the molecules in an object. So if we look at the kinetic energy of one object, or one molecule, and we have 50 molecules, then we take 50 times that energy, and we're going to get the total energy. So it depends not only on the average kinetic energy of a molecule, it also depends on how much mass that there is. The equation for internal energy U is 3/2 nRT. And it comes from the idea that U is going to be the number of molecules times the average kinetic energy of one molecule. So I can say that U is the number of molecules times 1/2 the mass of a molecule times its average velocity squared, which we learned is also 3/2 times Boltzmann's constant times temperature. Well, Boltzmann's constant is the same thing as the constant R over Avogadro's number. If I take and redistribute this whole thing, I end up getting 3/2 times, and I can say N, number of molecules, over Avogadro's number, times R times T, which is 3/2, and N over NA, the number of molecules over the number of molecules per moles, is going to give you the number of moles. So I'm going to get 3/2 N times RT, which is where this equation comes from. Now, heat is just simply the energy as it transfers from one object to another due to a temperature difference. If heat is being added to an object simply to raise its temperature, then the amount of heat, Q, can be found by taking the mass of the object times the specific heat of the object times its change in temperature. The heat is going to be in joules, the mass is going to be in kilograms, the change in temperature is going to be in degrees Celsius, and for us in physics, specific heat is going to be in joules per kilogram degrees Celsius. And on the right, you'll see some common specific heats. Like I said, we'll be using primarily the joules per kilogram degrees Celsius. And so the one that you're probably most familiar with is liquid water, 4,186 joules per kilogram degrees Celsius. I also would like to remind you that 1 kilocalorie is equivalent to 4,186 joules. Or in other words, it takes 1 kilocalorie of energy to raise water's temperature by 1 degree Celsius if I have 1 kilogram. The question is, if I add heat to an object, will its temperature always go up? And the answer is no. Sometimes we used heat to change the phase of an object. Which brings me to the phase diagram. If you take a look at this phase diagram for water, we have that 0 degrees Celsius is very important and 100 degrees Celsius is very important. And the reason that those two temperatures are very important is because 0 degrees is the melting point and 100 degrees Celsius is the boiling point for water. So you see that anything that's under 0 degrees is going to be in the solid form. And then anything between 0 and 100 is going to be in the liquid form, and anything above 100 degrees Celsius is going to be in the gaseous form. This phase diagram, also known as a heating curve, you can see that it's temperature versus heat. So as we add heat, what happens to the temperature? So as we start at solid ice, negative 40 degrees, as we add heat, we're simply just going to be raising the temperature of ice. And then we're going to keep adding heat, and the temperature is not going to be raising. That's because during this segment, the ice is going to be melting. And then once the ice is fully melted, now it's liquid water at 0 degrees Celsius. If we continue to add heat, the temperature of that liquid water is just going to get higher and higher and higher until we get to the next sort of critical temperature of 100 degrees Celsius. At 100 degrees Celsius, that's the boiling point. As I continue to add heat, what's going to happen is the liquid water is going to change to steam. And at this point over here, we are now at full steam, 100 degrees Celsius. If we continued to add heat, the steam would just get hotter and hotter and hotter. The equation to find the amount of heat required to change phase is given here. Q equals ml, where again, Q is heat energy, which is in joules. M is mass, which is going to be in kilograms. And then finally, L is the latent heat. And quite honestly, it's going to be the latent heat of fusion if it's melting, or the equation is going to be mass times the latent heat of vaporization if we're looking at changing it from a liquid to a gas. We can look at water to see that the latent heat of fusion of water is 333 kilojoules per kilogram. So we'll probably use joules per kilogram. So 333 times 10 to the third joules per kilogram. And then the latent heat of vaporization, 2,260, again, kilojoules per kilogram. So you're going to want to convert that to joules per kilogram when you use it in the equation. Going back to this phase diagram heating curve, on all of the line segments for which we're raising temperature, here, here, and here, that's going to go with the equation Q equals mc delta T. And so the mass is going to stay the same. The specific heat, you got to pay attention to that. That's trickier. The specific heat of solid water, ice, is different than it is of liquid water, which is different than it is of gaseous water, steam. So you do have to make sure you're using the specific heat for the correct phase. And then the change in temperature, remember, is also just going to be during that segment. So if I start at negative 40 degrees and I get to 0, then my change in temperature was 40. If I started at 0 degrees and I went to 100, then my change in temperature is 100. So I'm going to have to make sure I'm using that for that particular segment. The other part, when I'm changing phase, so here and here, those equations are going to be Q equals mL, where when you're melting, you're going to use latent heat of fusion, and when you're going from a liquid to a gas, it's going to be latent heat of vaporization. What I would like you to do at this point is try these next two problems. So pause the video, try the problems, and then you can go back and quickly watch to see if you did them correctly. Okay, so if we're predicting a temperature change, we're going to go with Q equals mc delta T. In other words, delta T equals Q over mc. And Q was given to us in kilocalories, which is fine. I can leave it in kilocalories, or I could have changed it to joules. The mass, well, the volume is 4,800 milliliters. We know that the density of water is 1 gram per milliliter, so we also have 4,800 grams of water. So that's 4.8 kilograms of water. And then the specific heat of water in joules per kilogram degrees Celsius is 4,186. But since I have kilocalories here, I know that the specific heat of water is 1 kilocalorie per kilogram degrees Celsius. So I'll save myself some time. And I end up getting that the increase in temperature is 3.1 degrees Celsius. In the second problem, we're supposed to predict the temperature change if 250 milliliters of water is heated with a hot pot for 45 seconds. Assuming 100% efficiency, that means assuming all of the energy that goes into the water goes in the form of heat, and it goes into the water only. So I know that power is the work or the energy divided by time. So the energy that I'm going to get out of plugging this thing in for 45 seconds is going to be the power times the time. So I can take 500 watts times 45 seconds, and that's how much energy in joules that I'm going to get out of the hot pot. That energy is 22,500 joules. And so that energy is now all going to be heat. So if I want to know the temperature change, if I use the same equation from above, it's going to be Q over mc. The energy, the heat energy that I got from the hot pot was 22,500 joules. The mass of water is 0.250 kilograms, using the same line of reasoning that I used in the previous question. And then the specific heat of water, since I'm in joules, 4186 joules per kilogram degrees Celsius. And I get that the change in temperature of that water should be 32 degrees. Heat can be transferred from one object to another in 3 different ways. 1, through contact. As the molecules collide with one another, they can give each other heat. That's called heat conduction. 2, convection. As you have mass movements of molecules from one place to another, that can move heat. And then finally, radiation, when you have transfer of energy through electromagnetic waves. One of the things that we're interested in is, particularly during conduction, what is the rate of heat that is transferred? And so the rate of heat that is transferred, H, is equal to the delta Q over T. But there's another equation that we can use, which is K. K stands for the thermal conductivity. It's characteristic to a material. And so you'll have a list of Ks that you can look at, thermal conductivity. And then times A, which is going to be the cross-sectional area, times the difference in temperature between the 2 points of interest, divided by L, the distance between those 2 points of interest, which is shown here. Since H, the rate of heat transfer, is delta Q over delta T, H's units is going to be in joules per second, which is equivalent to a watt. So H is going to be in watts. Here's a list of thermoconductivities. We'll be using the column here that says joules per second meters degrees Celsius, since we're going to be looking at energy in joules. If the thermal conductivity K is high, that means it's a good conductor of heat. And if it's low, that means it's a good insulator. So I want to think about a double pane glass window. Suppose that I had just a really thick piece of glass versus a double pane piece of glass like this. Here the median is glass, and here the medium, we have glass here, we have glass here, and then in between usually is filled with some sort of gas. For our it's air. I do believe that I think a lot of them are filled with argon, but let's say that air is the medium. Since air has a much lower thermal conductivity, 0.023, that means it's going to be a much better insulator of heat. And so as the cold air that's outside tries to get inside, that air is going to protect it from getting inside. Whereas if you have glass, which has a much higher thermal conductivity, which means it's going to conduct heat much better, that hot is, I said cold going to hot, but the hot air is going to be leaving much more easily because glass will allow it to. Okay, so again, I'd like you to take a look at the problem, try it, pause the video, try it out, and then press play again. Okay, so we have this concrete wall separating probably 2 rooms. So in the front of this wall is one room, and then behind the wall is another room, and so they're at different temperatures, those 2 rooms. We're supposed to find how much heat is transferred in 1 hour by conduction through this concrete wall. So one of the things we're going to need to know is what is the K for concrete? And the K for concrete is 0.84, according to the table, joules per second meters degrees Celsius. Okay, so I know that the rate of heat transfer, H, is delta Q over T, which is the same thing as K times A times the difference in temperature divided by the separation between them. And what I'm asked to find is what the Q is. So my Q, the amount of heat in an hour, is going to be K times A times T2 minus T1 over L times the time. So the K is given 0.84. The area that we're going to use is the area of the wall here, which would be 2 meters times 3.65 meters. And then we're going to multiply that by the difference in temperature, which is 15 degrees. I'm going to divide that by the length, which is really going to be the thickness of the concrete because that's separating the two different temperatures. So 0.2. And then finally, I'm asked to multiply that times the time. And so since our constant is, our K constant has seconds in it, then I'm going to need my time to be in seconds. So 1 hour, 3,600 seconds. And I end up getting 1.7 times 10 to the 6th joules is the amount of heat that is transferred from the hotter side to the colder side in an hour. Really quickly, one of the homeworks that you're going to do is a little bit tricky. There's this big long piece of metal, and half of it is copper and half of it's aluminum. And anyway, one side is held in a really hot area and one side is held in a really cold area. And the question is, what's the temperature in the middle? And what I would like you to remember so that it's a little bit easier to think about, the rate of heat transfer for the copper has to be equal to the rate of the heat transfer for the aluminum. In other words, the rate at which copper is going to lose heat is equal to the rate at which aluminum is going to gain heat. And so for the copper, you can sort of say that this end is the hot end and this is the middle. And for the aluminum, this end is going to be the cold end and this end is also going to be the middle so that they have this in common. Hopefully that helps. You're doing two things now at the lab tables. One is an activity, heat transfer. You're just going to take a sample of cold water and a sample of hot water. You choose the masses, mix them together, measure the final temperature. And you're going to calculate how much the hot water lost, how much heat the hot water lost, and then you're also going to calculate how much heat the cold water gained. Don't assume that it all went from one to the other, but calculate them based on the change in temperatures, and then you're going to take a look at the percent difference between how much one lost and the other gained. Do 3 different trials. And the second one is a lab. This one is just, you are supposed to figure out the latent heat of fusion for water. We do know it, so you can certainly compare to the known value. But you're going to do this by taking a sample of water, putting an ice cube in it, knowing the temperature of the ice cube before, knowing the temperature of the water before, and then finding the temperature after the ice fully melts. And from that, you're going to figure out what the latent heat of fusion of ice is. I will tell you, with this particular exercise, I want you to assume that all of the heat that was lost by the water went into the ice. So we can assume that none of the energy was lost to the surroundings in this experiment. But you have to decide how you're going to do that and do multiple trials.